In this hour, we will do for discrete time what we did for continuous time in the previous hour. Namely, we will study stability for a discrete time linear system. Okay. So let's remember our discrete time linear system. X plus equals AK X plus BK U, and the output Y reads CK X plus DKU. Okay, so let's call this system 1. This, remember, notation, X plus notation, simply means the value of X at the next time instant, and our time instants are denoted by K. Okay, this is our discrete time. It starts from 0 and it goes on through positive integers. K equals 0, 1, 2, 3, and so on. So this is the linear time varying discrete time system where the matrices A, B, C, and D are allowed to be functions of discrete time K. Okay. So in order to be able to study stability, first we have to be precise about what we mean by stability. And basically, so that means we have to introduce stability definition for discrete time, but it's just a straightforward extension of the continuous time definition. Okay, but still, for the sake of completeness, let's put that down. Okay. Now, system 1, the LTV discrete time system, is said to be okay, 1, stable, okay, in the sense of Lyapunov. Okay, or equivalently, internally stable, or they mean the same thing. If all the solutions in the presence of or in the absence of input remain bounded. If for each initial time, let's call it K0, and initial condition x K0 equals x0. x0 is our initial condition vector, and our system is of dimension n. Okay, n is the order of the system. The homogeneous state response, okay, which is the part of the response due to the initial conditions only. So we ignore the part coming from the input, we ignore the effect of the input. So in other words, x of k equals, so this is our initial time K0, and we consider the no input case. So we're dealing with this part, okay? X at the next time instant equals AK times x of k. We start at K0. At K0 plus 1, the value of the state is A K0 times X K0, okay? At K equals K0 plus 2, it's A K0 plus 1 times the value of the state at K equals K0 plus 1, and X K0 plus 1 is A K0 times X K0. So X K0 plus 2 is A K0 plus 1 times A K0 times initial condition. And if you keep on going, it's not difficult to see that X of K equals A of K minus 1 times A of K minus 2, and you go up to the initial time, okay, which is denoted by K0 times X K0, which is X0, where K equals K0, K0 plus 1, K0 plus 2, and so on. So if this response is bounded for all initial conditions and for all initial times, then this system is said to be stable. Clearly, stability definition, internal stability definition, does not care about the matrices B, C, and D. Okay, so the object of our study, therefore, is this matrix A of K. Okay, and for the time invariant case, this clearly boils down to, since all these matrices are the same, they're denoted by A, and here we have in this product we have k terms, so xk equals a raised to the power k times, supposing that k0 equals 0, because in that case we can take the initial time to be 0. So xk equals a raised to the power k times x at 0. So that what this expression boils down to for the LTI case. Okay. The system is said to be asymptotically stable if every solution, and by that we mean the homogeneous solution, okay, so we're ignoring the input solution to this difference equation, satisfies x of k converging to the origin as k goes to infinity. As k goes to infinity. And even a stronger version of stability is exponential stability, said to be exponentially stable if there exist constants one for the overshoot, the other for the decay rate, and lambda, which is between 0 and 1, such that the norm of the solution can always be upper bounded by an exponentially decreasing function times, or the scaled by, the initial norm. Okay, C lambda k minus k0 times the initial norm for k larger than k0 for all k greater than or equal to k0. Okay, k's are discrete time. And finally, if this first condition is not satisfied, the system is said to be unstable. Okay, so a system is unstable if not stable. So that's the definition for the general case in LTV system. So from this point on, what we will do, we'll study the LTI case. Okay, x plus equals a times x. And we already studied the behavior of the so-called state transition matrix, a to the k, okay? In continuous time, this is our state transition matrix, and in discrete time, it's a to the k. We studied the evolution of this discrete time state transition matrix, a to the k, based on the eigenvalue locations of the A matrix, okay? And our findings were, thanks to the Jordan form decomposition of the A matrix, our findings were as follows. If all the eigenvalues of the A matrix, okay, are such that their magnitudes on the complex plane, their magnitudes are strictly less than 1, then a to the k converges to 0, always, as k goes to infinity. If you have at least one eigenvalue of a whose magnitude is strictly larger than 1, then a to the k blows up exponentially. And if neither of those conditions are satisfied, then what you do is you look at the eigenvalues on the unit circle. So what imaginary axis is for continuous time, its analog is unit circle for discrete time. So you look at the eigenvalues on the unit circle, and for each of those eigenvalues you look at the corresponding Jordan blocks. If the Jordan blocks are all size 1 by 1, then you can deduce that a to the k as k goes infinity. It may not converge to 0, but it will at least remain bounded. If you have one eigenvalue, at least one eigenvalue on the unit circle, whose Jordan block is size 2 by 2 or larger, and then a to the k as k goes infinity, will have a growing, unboundedly growing norm. Okay, so based on those qualitative studies on the behavior of a to the k and the locations of the eigenvalues of a, we can now write down our first theorem. Okay, and we wouldn't need to prove it because we have already proven it in a sense. Okay. The LTI system, x plus equals ax. Now a is a constant n by n matrix, n the order of our system. Okay, and we're studying internal stability, or stability in the sense of Lyapunov. Therefore, studying the stability of this system, or the more general representation where we have B, C, and D matrices, is equivalent. Okay, so because of that equivalence, for simplicity, we study this homogeneous difference equation. Okay, so this system is, according to our definition, stable. Okay, if and only if A. Now, based on our studies on the behavior of a to the k, we can write the following. If we have no eigenvalue whose magnitude is larger than 1, okay, in other words, all the eigenvalues are on the unit disk for all I, okay, and lambda I, they indicate the eigenvalues of A. And if you have an eigenvalue on the unit circle or on the border of the unit disk, that is, if the magnitude equals 1, then what you do is you go and check the corresponding Jordan block. If all the Jordan blocks for eigenvalues satisfying this property are of size 1 by 1, then your system is stable in the sense of Lyapunov. This implies size of the corresponding Jordan block is size 1 by 1. Okay. 2, asymptotically stable. Okay. So this homogeneous difference equation is asymptotically stable, and for the LTI case, which we are studying, it's equivalent to exponential stability. Okay. If and only if all the eigenvalues are with magnitude strictly smaller than 1 for all indices I. Okay, and finally, it's unstable. Okay, now this is the stability definition, and it's if and only if type. Therefore, this completely characterizes stability of our system x plus equals a of x. And since unstable means not stable, all we have to do to figure out the condition here is we have to negate this statement. Okay, so therefore, if and only if either, okay, there exists an eigenvalue such that its magnitude is strictly greater than 1, or there exists an eigenvalue on the unit circle for which the corresponding Jordan block is of size 2 by 2 or larger. And the size of the Jordan block corresponding to that eigenvalue is of size 2 by 2 or larger. Okay. So that's the complete characterization of stability properties of our LTI system in terms of the eigenvalue locations on the complex plane. Okay. To compare the definitions of stability for systems in continuous time and discrete time, to make a link between those two cases, let's consider the following example. Okay. Suppose that we have a continuous time system, LTI. X that equals AX. And the solution to that system is x of t, which equals e to the at, state transition matrix, times the initial state, x0. Now, one way to discretize the system, in fact, the simplest way, okay, sometimes it's too simple, it's not accurate enough, but sometimes it works well enough so that it's sufficient. It's a successful approximation. It depends on the application. And that simple discretization method is Euler discretization. Okay. Which is the following. Now, from that continuous time, we generate a discrete time system whose state is denoted by z. Okay. X is in Rn. Z is also in Rn. They're of the same size. And how we obtain that discretization is zk plus 1 equals the value of the state at the previous time, and then you add epsilon times a times zk. Okay. Now ax is sort of the velocity vector at point x. So what we do is we start from z of k and we move for a while at velocity azk. Okay. And epsilon is called the step size. Epsilon positive is the so-called step size. Of our discretization. Okay. And now we have moved from continuous time, where the time variable is denoted by t, to discrete time, where the time variable is denoted by k. K takes, as we all know, integer values, 0, 1, 2, 3, 4, 5, and so on. Okay, now what's the relation between the evolution of this discrete time system, z of k, and this continuous time system, x of t? It's as follows. If you start from the same initial conditions, if z0 and x0, they are the same, then z of k, okay, these values, z1, z2, z3, and so on, which are generated based on that difference map, okay, difference equation, they correspond to approximately the values of the solution at the particular times. Okay, so z0, z1, z2, and so on, those values of our discrete time system state approximately equals the value of the actual solution at t equals 0, at t equals epsilon second, at t equals 2 epsilon seconds, and so on. Okay, and this is a good approximation, more or less, provided that epsilon is small enough. Okay, and how small, it depends on the application, and also for k small enough. Okay, if you go farther and farther, the difference between the approximation and the actual state will become larger and larger. Okay, in general. Anyway, so this is a good approximation for epsilon and k small. Okay, now this is more or less clear intuitively, but let's also try to make it more or try to quantify this claim here, okay, to make it look more rigorous. And for that, let's write down the solutions explicitly, or more explicitly. Okay. Now we try to answer this question, why this is a good approximation, at least for epsilon k small. Here is why. Now z plus equals, discrete time system can be written as, note that this right hand side can be written as identity matrix plus epsilon times a, and that matrix is multiplied by zk. So we have this type of discrete time system where the A matrix is identity plus epsilon times A Z. Okay, so this is the A matrix of our discrete time system, where this A matrix is coming from the continuous time system, for which this is an approximation. Now this implies that Z of k equals, so Z of Z1 equals this matrix times Z0. Z2 equals this matrix times Z1. And Z1 was this matrix times Z0. Therefore, Z2 is this matrix squared times Z0. And in general, Z of k is this matrix, okay, raised to the power k times Z0. I plus epsilon A raised to the power k times the initial state, Z0. Okay, and how about x at time k times epsilon? This equals e to the a t, where t is k times epsilon, times x0. Okay, and this can be written as e to the a epsilon raised to the power k times x0. Okay. By the way, this matrix here, e to the a epsilon, would be the exact matrix for the exact discretization of our continuous time system. Okay. So therefore, we have this equality sign here to the k, and let's write this in open form, e to the a epsilon. That can be written as identity plus epsilon a plus epsilon square over 2 factorial a square plus epsilon cube over 3 factorial times a cube, and so on up to infinity, raised to the power k times x0. And now once it's written in that form, it's clear more or less that for epsilon small, we can ignore, for the first approximation, the higher order terms of order 2 and larger. So this thing equals approximately identity plus epsilon times a for epsilon sufficiently small. Okay, therefore this approximately equals plus epsilon a raised to the power k times x0. Okay, now it's clear that if you start two systems from the same initial conditions, z0 equals x0, xk of epsilon would be approximately equal to that, and z of k would be exactly equal to that. Therefore, the two solutions, z of k and x of k epsilon, would be close to one another. Okay, for for epsilon and k small. Now let's try to make a link, if we could, between the stability properties of the actual system, continuous time system, and its Euler discretization. Let's see whether the stability properties of the continuous time system is inherited by the approximation, Euler discretization. Okay, in other words, we will now attempt to show that for an exponentially stable system, its discretization, Euler discretization, is also exponentially stable, provided that epsilon is not too large. And while showing that, we will have a chance to compare the eigenvalues of two systems in terms of one another. Okay, so now we continue with our example, and we'll try to show that if the continuous time system is asymptotically stable, equivalently if it's exponentially stable, because we're dealing with the LTI case, then its Euler discretization Euler discretization, it's here, for which we denote the state by z, is also exponentially stable, provided that the step size is small enough for epsilon small enough. Okay. Let's do this through the eigenvalues, okay? Through the comparison of the eigenvalues. Now we have continuous time system, x that equals ax, whose eigenvalues we denote by, let's say, lambda I, okay? And since that system is given to be exponentially stable, we know from our earlier theorems that these eigenvalues are on the open left half plane. In other words, for each I, or for all eigenvalues, real parts are strictly negative. Okay, so that's the continuous time system. And now this is the approximation in discrete time, or the simplest approximation in discrete time. Z plus equals identity plus epsilon A Z. And eigenvalues, let us denote them by alpha I. Okay. Now, since we know stability in terms of the eigenvalues for both continuous time and discrete time case, we can now rephrase the problem as follows. Suppose that x that equals ax, okay, or suppose that the eigenvalues of A all satisfy this real part of lambda I strictly less than 0. Then for epsilon small enough, the eigenvalues of this matrix all satisfy the condition of exponential stability in discrete time. That is, all of them have magnitudes strictly smaller than 1. Okay, so from this we will try now to reach this, provided that epsilon is small enough. Okay, so this is what we want to show. So what's alpha I in terms of lambda I? Let's first try to answer that question. Let Vi be the eigenvector for the ith eigenvalue of the A matrix, okay, lambda I. In other words, This vector is a non-zero vector and it satisfies the following eigenvalue, eigenvector equation, lambda I, vi. Now, it's not difficult to see that this eigenvector must also be eigenvector of identity plus epsilon times A. Why? Because all we have to do is just multiply our discrete time matrix by the same eigenvector. Vi equals, we have Vi plus epsilon A Vi. That's Vi plus epsilon. Now A Vi is lambda I Vi. So here we have lambda I Vi, and that can be written as 1 plus epsilon lambda I Vi. Okay. Here we have another eigenvalue, eigenvector equation. This matrix times Vi equals this scalar times Vi. Therefore, this scalar must be the eigenvalue, an eigenvalue of this matrix. And the eigenvalues of this matrix are denoted by alpha I. Therefore, alpha i's must have the following form: 1 plus epsilon lambda I. Okay, now we have got one step closer to what we want to show. Now what we want to show is the following: if lambda I satisfy this, then for small epsilon, this thing alpha I satisfies that condition. Okay, that requires just a little bit of work, but let's do that. It's because it's worth it. Let me first write lambda I in rectangular coordinates. So we can write lambda I, which, since possibly a complex number, it will have a real part and an imaginary part. So in general, we should be able to write it as follows: plus j omega I, with delta and omega both real, and delta must be positive because real part of lambda I is negative. Okay, real part of lambda I is minus delta I, with delta I a positive real number and omega I is just an arbitrary real number. Okay. Now, let's concentrate on this norm. It's easier to work with norm square because if this is true, then this is also true. Therefore, for notational convenience, let's work with the absolute value square, or the magnitude square of alpha I. So, alpha I magnitude square equals 1 plus epsilon lambda I, and lambda I we now write it as j omega I square. Okay, and that equals, the real part is 1 minus epsilon delta I, and the imaginary part is j epsilon omega I. So we can write 1 minus epsilon delta I, the real part square, plus the imaginary part square, which is epsilon square omega I square. Epsilon square omega I square. Okay, so that's the magnitude square of our eigenvalue. Eigenvalue of what? Eigenvalue of the discrete time system. Okay, so that thing can be written as 1 minus okay, 1 minus epsilon delta I, or 2 epsilon delta I, plus epsilon square delta I square plus omega I square. Okay, so we just wrote the square this here in open form, and then we collected certain terms. And this, okay, can be written as 1 minus epsilon delta I, okay, minus epsilon delta I minus epsilon delta I square plus omega I square. Okay, again we made another reorganization. Here we have minus 2 epsilon delta I. We let one of them stay here, and we transferred the other half to this side here, so that by playing with the epsilon we can make this thing larger than 0. Therefore this would be smaller than 0. It will be a negative, and the overall thing will be smaller than 1. Okay, and that's what we want. Okay, what we want now is we want to show that by choosing epsilon small enough, we can make this thing positive, and eventually the whole thing negative, and then eventually the whole thing smaller than 1. So delta I minus epsilon delta I square plus omega I square. Okay, so we want this to be positive, and that's equivalent to epsilon being smaller than delta I over delta I square plus omega I square. Okay, which equals real part of lambda I magnitude divided by lambda I magnitude square. Okay. Now, by choosing epsilon smaller than this fraction for all indices I, or for all eigenvalues of A, I equals 1 to n, the real part of lambda I divided by lambda I magnitude square. Okay, then we can guarantee the following: alpha I magnitude square less than or equal to 1 minus epsilon delta I. Okay, now since this is positive, this whole thing is negative, therefore this is less than or equal to this thing here. Okay, the norm square is less than or equal to 1 minus epsilon delta I, which clearly is smaller than 1 for all indices I. Okay, then since magnitude square is strictly less than 1, it must be that magnitude is strictly less than 1 for all I, and as a result, thanks to our previous theorem, the discretization is exponentially stable. Is exponentially stable. Okay? Therefore, exponential stability property of a continuous time system is inherited by its Euler discretization, provided that the step size is small enough. Okay, this brings up the question: what can we say about just stability? Okay, so that would be a nice exercise, and we cannot, it turns out, extend this result to the stability, meaning that there are certain continuous time systems that are stable, such that for such systems, no matter how small you choose your step size, the Euler discretization will always turn out to be unstable. Okay, so that's a nice theorem, or that's a nice statement to think about for those of you who have time. But we have to move on, and so we close the subject here. In the previous lecture, we had the Lyapunov characterization of exponential stability for continuous time systems. Now, in the remaining part of this hour, we will talk about the same theorem, but this time for the discrete time system. Okay. Lyapunov stability theorem for the discrete time system. For the LTI system x plus equals ax, the following 5 conditions, and those 5 conditions are directly coming from, or they are the direct analogs of the 5 conditions that we considered in the previous hour. The following conditions are equivalent. Okay. One, system is asymptotically stable. Okay. 2, system is exponentially stable. Okay, we know that they're the same thing for an LTI system. 3 is the eigenvalue characterization, which comes from our first theorem this hour, namely all the eigenvalues lie in the open unit disk, or they are with magnitude strictly less than unity for all I. Okay, lambda I is the eigenvalue of the matrix A. Okay, and now we have the Lyapunov characterization part of our theorem. For each symmetric positive definite matrix Q, we can find another matrix P, which is the unique solution P in Rn by n. So by the way, here x is in Rn. Okay. Therefore, n is the order of our system. To the following equation, okay, which is sometimes called the Stein equation, or discrete time version of the Lyapunov equation. Stein equation, or discrete time Lyapunov equation. ATP A minus P equals minus Q. Okay. Remember the Lyapunov equation for continuous time. It was ATP plus PA equals minus Q. Now for discrete time, that equation is transformed into this different looking equation. Okay. And moreover, as with the case with continuous time, P is symmetric and positive definite. Moreover, P equals P transpose, and it's positive definite. And finally, 5, there exists P equals P transpose. Okay, a symmetric positive definite matrix of size n by n, satisfying ATP A minus P less than 0. So this means that we can find a P symmetric positive definite such that this matrix n by n, ATP A minus P, is negative definite matrix. Okay. Now the proof, at least the roughly speaking, or from the qualitative point of view, is the same as the proof in continuous time. Note that how we obtained that, or the P that solves the Lyapunov equation in continuous time was that we had a candidate, and that candidate was you take Q, multiply from left and right by transpose of the state transition matrix and state transition matrix, and then you integrate that integrand from 0 to infinity. Okay, so what we had is P equals from 0 to infinity e to the a transpose t q e to the at dt. And this time what we have is, although we're not going to prove it, but you can prove it with this P very easily, we're going to do the same thing. Okay, now instead of integration, since we're in continuous time, we have summation k equals 0 to infinity. Instead of e to the at, we have the state transition matrix in discrete time. Therefore, a to the k transpose q, a to the k. Okay, with this P, it's not difficult to show that Stein equation is satisfied, and furthermore, we have the other conditions as well. Okay. But still, even though we're not going to provide the entire proof, let's just talk about a part of the proof so that we have some idea how, or some geometric idea between the relation of P and the decrease of the, or the convergence of the solutions to the origin. Therefore, in our next example, we will prove a part of the Lyapunov's theorem. Namely, we will show that 5 implies 2. Okay. This is our next example, which is basically part of the proof. Let's show that 5 implies 2. Namely, if you can find a symmetric positive definite matrix which produces, when written in this form, a negative definite matrix, then your LTI discrete time system x plus equals ax must be exponentially stable. Okay. Now, for the system x plus equals ax, suppose there exists a symmetric positive definite matrix P transpose positive definite, and P is of size n by n. N is the order of our system, satisfying Stein's inequality. ATPA minus P is a negative definite matrix. Now, starting from that premises, we're going to show that the system has to be exponentially stable. Okay, here is the nice, I think, elegant solution. Let us define Q as minus this matrix. In other words, P minus ATPA. Okay. Now, since ATPA minus P is negative definite matrix, this Q introduced must be a positive definite matrix. Now, given any solution of the system x plus equals ax, x of k to x plus equals ax, define the following scalar function of the discrete time k. So we define v of k as xk transpose pxk. Okay. And since P is a positive definite matrix, and at any time this is just a vector, by definition, this scalar must be non-negative. Okay. So this is always greater than or equal to 0, because P is a positive definite matrix. Now, we did the same thing until this point for the continuous time. Okay. For the continuous time, this system x equals ax, we have started with a solution, an arbitrary solution, x of t, and using that solution and p, we constructed the scalar function v of t, which was x of t transpose p times x of t. And then what we did in continuous time is we differentiated this with respect to time and evaluated v dot, and we showed that v dot was negative. Okay. Now we're going to do the same thing, almost the same thing. Okay. In continuous time, we differentiated this function v, and now we're going to differentiate this in discrete time sense. Okay. So analog of differentiation in continuous time is one step difference in discrete time. Okay, so we're going to apply that one step difference thing to v of k. Namely, we're going to subtract v of k from v of k plus 1. So let's do that. Okay, so let's do that here. V of k plus 1 minus v of k. So this is, in a sense, differentiation in discrete time. That equals xk plus 1 transpose p xk plus 1. This is v of k plus 1 minus x of k transpose p x of k. Okay. And that can be written as xk plus 1 is a times xk. Okay, from the difference equation. So this can be written as xk transpose a transpose p a x k minus xk transpose p x k. Okay, this is xk plus 1 and this is xk plus 1 transpose. Now, since both terms are multiplied from left and right by xk transpose and xk, we can write this as xk transpose times something times xk, and that something is ATPA minus p, an n by n matrix, ATPA minus p. And what's ATPA minus p? It's minus q. So this therefore equals minus xk transpose q xk. Okay, using the upper and lower bounds in terms of the eigenvalues of matrix Q, this can be written as, not that we did that trick many times for the continuous time demonstration, this can be written as minus lambda min Q and then norm square of xk. Okay. And then we apply once again that trick, this time to the matrix P, and upper bound minus norm square of x by minus x transpose px divided by lambda max p, and that produces minus lambda min q over lambda max p times xk transpose p times xk. Okay, and this is no other than our function v. So what we have obtained is this difference is less than or equal to minus something times v. Okay, so let's write it down cleanly here. So what we have obtained, therefore, is Vk plus 1 minus Vk, discrete time derivative of V, okay, is less than or equal to minus epsilon Vk, okay, where epsilon is defined as this ratio, a positive number, where epsilon is lambda min q over lambda max p, which is positive, because this is positive and that's because both p and q are positive definite symmetric matrices. Okay, by definition they have all positive eigenvalues, positive real. Okay, so that's epsilon. What we do from what we go from here is as follows. We're almost done. What we do is we carry this v of k to the other side, and then we have vk plus 1 less than or equal to, okay, vk minus epsilon vk, so that produces 1 minus epsilon vk. Okay, now let's introduce one further notation. Let alpha be equal to 1 minus epsilon. Okay. Note that alpha must be smaller than 1 because epsilon is positive, and it cannot be negative because if alpha is negative, this thing is alpha. If alpha is negative, V is always positive because it's defined through a positive definite matrix. Then what we would have is negative positive, so that makes negative, and this thing is less than or equal to something negative. Therefore, this would be negative, but this cannot be negative because it's defined through a positive definite matrix. So therefore, alpha cannot be negative, and it's somewhere in this region, 0 and 1. Okay, so this implies what? So this is now alpha. Okay, this implies V1 less than or equal to alpha times V0. V2 less than or equal to alpha times V1. V1 is less than or equal to alpha times V0, therefore V2 less than or equal to alpha alpha times V0. And if you go on like that, it's not difficult to see. And we can write V of k less than or equal to alpha raised to the power k times the initial value of our scalar function V0. Okay. So then we proceed as follows. Norm square of the solution less than or equal to 1 over lambda min p xk transpose p xk. Okay, we use once again those identities that relates this form with the norm square of the Euclidean norm and relates them through the eigenvalues of p. So that's what we have. The reason that we have written this is because here we have the function v. Okay, so this is v of k, and v of k is less than or equal to alpha to the k v0. So therefore, this thing is less than or equal to alpha to the k lambda min p times v0. This is v0. Okay, and that's less than or equal to, again, one of those norm tricks, lambda max p, lambda min p, alpha k, norm of x0 squared. Okay, and all that remains is to take the square root of both sides, and that produces norm of the solution can be upper bounded by lambda max p over lambda min p square rooted times square root of alpha to the k times the initial norm of the solution, x0. And this, by definition, means that the norm of the solution is less than or equal to c times, okay, lambda to the k, and lambda is less than 1 times the initial norm. Therefore, by definition, we have exponential stability of the system, which was to be shown.